Welcome back, everyone. This is Mr. Bowman again for the second part of these notes on 2.6, day 1. We're going to talk about horizontal asymptotes and how to determine what they are. And we're going to talk about finding x and y intercepts. And then we're going to practice with a few problems. So, how do you find horizontal asymptotes for rational functions? It's really straightforward. All you have to do is look at the ratio of the highest degree terms. So find the highest degree term in the numerator, find the highest degree term in the denominator, simplify those, and then think about what happens to that as x approaches positive and negative infinity. So there are three cases that can arise for rational functions. You can have the case where the numerator has a smaller degree or a lower degree than the denominator. In that case, the end behavior, or the limit as x approaches either plus or minus infinity of f of x, is going to be 0. The second case is if the numerator and denominator are both the same degree, then the limit as x approaches plus or minus infinity of f of x, and f of x is our rational function, is going to be some constant. And you saw that in the last video. And then finally, if the numerator is a higher degree than the denominator, then the limit as x approaches plus or minus infinity of f of x is either going to be positive infinity or negative infinity. So let's take a look at a few examples. So here's an example where we have a rational function and we want to find the end behavior. So we ignore everything else except for the two highest degree terms. And the reason we do that is because when x gets extremely large, either goes towards positive infinity or goes towards negative infinity, the two terms that have the biggest impact on the numerator and denominator are the highest degree terms. Think about if you're squaring something as opposed to not squaring it, only keeping it to the first power. So we look at the ratio of the two highest degree terms, x over x, which simplifies to 1. And basically what we can say is the limit as x goes to plus or minus infinity, I'm putting them both down here because they're going to be the same, of f of x is equal to the limit as x goes to plus or minus infinity of x over x, or 1, which is 1. In our second example, highest degree term in the numerator is the constant 1, and the denominator is x squared, and the limit as x approaches plus or minus infinity of f of x, our rational function, is going to be whatever 1 over x squared does as x gets very large. And when I say large, I mean large in magnitude. X is approaching either positive or negative infinity. So all you have to do is think about that for a moment and think about making x get very, very large. 1 over x squared is going to get very, very small. So our end behavior is not infinity like I wrote down, it's 0. In other words, as x goes towards positive infinity, y goes towards 0. As x goes towards negative infinity, y goes towards 0. Next, we'd like to talk about intercepts. So y-intercepts. Y-intercepts are the same for, or finding y-intercepts is the same for any function. It is the value of y, or f of x, when x is equal to 0. So in other words, or that is, the y-intercept is always equal to whatever f of 0 is. So you want to find a y-intercept, plug in 0, simplify, and you've got your answer. x-intercepts, on the other hand, are the value, sorry, not the value. Let me start that over again. The real zeros of only the numerator. In other words, don't worry about the real zeros of the denominator. Find the values of x, the real values of x, that make the numerator equal to 0. Now, if it's a value of x that makes the numerator and denominator equal to 0, technically that's a removable discontinuity. So that is not a x-intercept. So let's finish up with a little bit of practice here and put all this stuff together on the next page. We will start with a relatively simple rational function and start finding all the things that we need to find. So vertical asymptote, where the real zeros of only the denominator, or where x minus 2 is equal to 0, so that would be at x equal 2. The x-intercept, where only the numerator is equal to 0, and that would be at x equal -3. The y-intercept is the value of f when x is equal to 0, or the value of y when x is equal to 0, and you will see that simplifies to -3/2, or -1.5. Well, we're going to also describe the behavior of this function using limits, and probably the easiest way to do that is by graphing it. So what we're going to do is we're going to start out by making our sign chart, and we are going to put 2 in here. We want to see what happens on either side of x equal 2. So let's plug a number less than 2 in, like 1.9. 1.9 plus 3 is going to be positive. 1.9 minus 2 is going to be negative. So to the left of 2, x equal 2, our graph is going to approach -infinity. And let's pick a number slightly greater than 2, like 2.1. 2.1 plus 3 is positive. 2.1 minus 2 is positive. So that result is positive, which means to the right of x equal 2, our graph is going to approach positive infinity. Now, for the horizontal asymptotes, look at the ratio of the highest degree terms. So x divided by x, which is equal to 1. So the limit as x approaches both plus and minus infinity of f of x is equal to 1. Now, the reason I can write that as both plus or minus infinity is because it is approaching the same value on the left and the right. If, for example, the rational function is going off to positive infinity or negative infinity for n behaviors, you may not be able to write it that way. If they approach different values, you can't write it that way. So now let's finish up by graphing this and then write our vertical asymptote limits. So here we go. We've got the y-axis. We've got a vertical asymptote at x equal 2. Very often asymptotes are represented with a dotted line. We've got a horizontal asymptote at y equal 1. And we have an x-intercept at -3, 2, 3. Okay, a y-intercept of -3/2, so that's about right there. And we know that our function goes towards -infinity as we approach +2 from the left. We know our graph has to go through our y-intercept. Graphs always go through y-intercepts. And another thing you can do is you can use what you learned from polynomials here, and the multiplicity of the 0 is 1. X plus 3 factor only occurs once, so we know our graph is going to cross the x-axis at x equal -3, and it's going to approach y equal 1 as we go towards -infinity. And then the only other part we have to graph is the part to the right of our vertical asymptote, x equal 2. Well, we know from our sign chart that the graph approaches positive infinity as x approaches 2 from the right hand side, and we also know from our end behavior limit that the graph, or y, approaches 1 as x goes towards positive infinity. So we have to write down the limit notation for our vertical asymptotes. So as x approaches 2 from the left, f of x approaches -infinity. As x approaches 2 from the right, f of x approaches positive infinity. All right, for our last example here, this one's a bit challenging because if you look at the numerator, you will see that x squared minus 3x minus 7 is not factorable. So finding the zeros is going to be a little more challenging. Finding the x-intercepts is going to be a little more challenging. We're going to have to use the quadratic formula on that. So let's start with that. X is equal to 3 plus or minus the square root of 3 squared, which is 9, minus 4ac, or plus 28, all divided by 2, which simplifies to 3 plus or minus the square root of 37 divided by 2. Now, we're going to want to graph this thing eventually, so we're going to have to estimate what these x-intercepts are. Square root of 37 is approximately 6, so effectively we're going to estimate our x-intercepts at 3 plus or minus 6 divided by 2, which are approximately equal to, let's see, -3 halves. Again, these are approximations. Or positive 9 halves, which are approximately, again, those approximately -1.5 and positive 4.5. And those also have multiplicity of 1, so our graph will cross the x-axis at those approximate values. So let's label those as x-intercepts. Y-intercepts. Well, the y-intercept is equal to f of 0, and f of 0 is -7 over -4, which is positive 7/4, which is equal to 1.75. Vertical asymptotes. Vertical asymptotes, where the real zeros of only the denominator. Well, we can see that the denominator factors into x plus 2 times x minus 2, so we have vertical asymptotes at x equal plus or minus 2. We have 2 of them. And now we're going to make a sign chart and see how our graph behaves so that we can write the limit notation. So let's see. Our sign chart is going to go like this. We're going to have -2. I am going to put the zeros in, or the approximate zeros in, -1.5, positive 2, and 4.5. And the reason I'm going to put the zeros in is because the graph is going to cross the x-axis at those zeros. So, for example, at our vertical asymptote of -2, if the graph goes towards -infinity, as we approach positive 2, the graph should cross the x-axis and approach positive infinity, but we'll go ahead and verify that. All right, let's pick a number slightly less than -2. And this gets a little bit complicated here because we're going to have to estimate the value of the numerator if it's positive or negative. So let's say -2.1. We square that, that's going to be about positive 4. Negative 3 times negative 2.1, that's going to be about positive 6. And then we subtract 7 from that. So we've got a roughly positive 4 plus a roughly positive 6 minus a 7. So the result is going to be positive. In our denominator, it's a little bit easier. If we put it in factored form, x minus 2, x plus 2. So negative 2.1 minus 2 is negative. Negative 2.1 plus 2 is negative. And the result is going to be positive. All right, let's pick a number slightly bigger than negative 2.0. Negative 1.9. Again, we're going to have to estimate the numerator. If you do that, you will see that the numerator is going to be positive. The x minus 2 factor is going to be negative. The x plus 2 factor is going to be positive. So we're going to have a positive divided by a negative, and that's going to give us a negative. Now, again, we said that our graph will cross the x-axis here at roughly negative 1.5. So our vertical asymptote at positive 2, what we should see is on the left-hand side, y should go towards positive infinity, but let's verify that. So a number slightly less than positive 2, like 1.9. 1.9 squared in the numerator is going to be roughly 4. Minus 3 times 1.9 is going to be roughly minus 6. Minus 7. The result is going to be negative in the numerator. 1.9 minus 2 is going to be negative. 1.9 plus 2 is going to be positive. So we have a negative over a negative, and it is positive. That confirms what we suspected. And finally, as x approaches positive 2 from the right, let's pick a number like 2.1. 2.1 squared is going to be positive. Minus 3 times 2.1 minus 7, the result is going to be negative. 2.1 minus 2 is going to be positive. 2.1 plus 2 is going to be positive, so we have a negative divided by a positive. The result is negative. All right, we don't have enough room to graph this thing here, but I highly suggest that you do. Put that in your calculator and verify that our sign chart is correct. We are, however, going to finish up by writing these limits, and there's quite a few of them. The limit as x approaches both plus and minus infinity. Oh, we didn't do that yet. Well, x squared over x squared is 1. So as x approaches plus and minus infinity of f of x, the result is going to be 1. The limit as x approaches negative 2 from the left is going to be positive infinity. The limit as x approaches negative 2 from the right is going to be negative infinity. The limit as x approaches positive 2 from the left is positive infinity, and the limit as x approaches 2 from the right is negative infinity. I highly suggest that if you are struggling with this last problem, you graph this on your graphing calculator and you verify what is happening near at the end behavior and what's happening near the vertical asymptotes.